or how many people have not seen me about a project? Raise your hands. Have not seen me. All right, if you have not seen me or talked about it, please try to get to this before Thanksgiving. That's what I'm asking you to do. Just
Can we email you?
Huh?
Can we email you about it?
Yeah, if you, but I prefer, because I got one person sent me something, and I think it was you, and because it was a short explanation, it sounded like what he was going to do is just inverse, like it was shielding effectiveness. You're going to tell me a thickness if I wanted a certain shielding effectiveness. Yeah, you can do that, but that's not really much of a problem to do. I can talk to you afterwards. I got an idea about how to make that a little more difficult. But try to send me something or try to come to me with an idea. I'm pretty much green lighting everything, all right? As long as it's not, something really bizarre. But I appreciate if you get this to me before break, all right? And everybody's going to have to turn in one of these or you're going to fail. So that's your motivation. I've never said anything quite like that before, but this time I'm going to say that because that way I'll get 100% compliance. Or I'm going to have somebody here that's really in for a shock. Anyway, all right, that said, now today we're going to be talking about the scattering parameters. How many actually took a look at these problems and tried them? Most of them are not hard. If you have not looked at them, I suggest you do and you go along and work with me on this because scattering parameters is something you're going to be using almost all the time for high-frequency microwave engineering. As a matter of fact, right now, I'll tell you, most high-frequency amplifiers, transistor amplifiers and stuff, they're not the transistor themselves, usually have it's an HFE and all that stuff, those parameters, the H parameters. Those are translated into S parameters almost all the time for the engineering purposes. So now for S parameters. And I got to ask you, does anybody have any questions before I start? At all? Okay. Because if you do, I'll try to take them at the beginning of class. If no questions, then we're going to go ahead and start with the scattering parameters and continue working on those things. So again, the S matrix is given as S11, S12, S21, and S22, right? And in general, it's usually V1 minus V2 minus, this is the actual way it's blocked, is equal to S11, S12, S21, S22, and then times V1 plus, V2 plus. And it's for ports, so this is just a two-port problem. So there's a plus to minus. Signal going in is V1 plus. Signal coming out this way is V1 minus. Here, this is port 1. Here at port 2, you've got V2 minus, and you've got V2 plus into there. And the voltage is always measured across the transmission line. This is considered a transmission line. It could be a waveguide, to be honest with you. A lot of times it's waveguides that feed these things. So now that that's set, it wouldn't be now that I'm talking about that, now I want to get into examples so everybody understands this. So if we take a look at the definition of S11, this is really V1 minus over V1 plus, given that V2 plus is 0. So what's a typical problem you run into? If you haven't looked at it, it's a good time to pay attention because this is a good example. Even though it's extremely simple, it's a very good example. So here, I'm going to go ahead and take some transmission line with Z0 here. Then I'm just going to go ahead and put a given resistor R there. And he does this problem in the book. And put Z0 here. Now, if I make Z0 equal to, say, 100 ohms, I think this is the one in the book, and make this 50 ohms, that's where my S parameter matrix would literally be placed, if you were thinking about it. That's where the port is. This is port 1, and this is port 2. Now I want the scattering parameters that's going to be related to that. Now, the thing about this one is, I'm assuming that this thing's going into a matched load. Do y'all follow me on that? And if it's going into a matched load, then there is no V2 plus. There's nothing coming into that port 2, all right? So we've established this condition is present. Follow me, class? Once that's present, really you're talking about the reflection coefficient there. So what is the reflection coefficient here? And the way you look at this, I'm going to break it down for you. Nice thing about this problem, it's reversible. The S22 is the same as S11. If you flip that around, it's the same exact circuit. You follow me? And that's good, because that means now, when we look at S11, what we're really doing is taking a look at the reflection coefficient in port 1. And the way you're going to have to do this is you have to draw an equivalent. So this is going to be the 100 ohm line right here. Now you have a 50 ohm resistor here, but now you have 100 ohms over on that side, so you drop down a resistor here, 100 ohms. This effectively models that transmission line. Everybody follow me on this? And you have to make sure you see this. Now if I want the reflection coefficient right here, that is S11. Well, I need the impedance I see in there, right? So the impedance I see in there, looking this way, would be Z equals 150 ohms. Do you all see this? And the way I tell people to do these problems, it's just like shielding problems. It's the impedance you see going in to the port divided by the impedance you came, or subtracted from the impedance you came from, over the sum of the two. So here, the impedance I'm going into, you all see 50 and 100 is 150, right? So it's going to be 150 minus the impedance I came from is 100, right? And then, I'm sorry, 50. It was 50, wasn't it? No, I put it as 100. We'll do it with 100. Over, and then the sum of these two is going to be 250. So that means S11 for this one is going to be simply 50, right? Over 250, or it's 1/5. That would be the S11, the reflection coefficient. You agree with me, class? How many see it's that S11 is necessarily S22? S22 will be equal to V2 minus over V2 plus, with V1 plus equals 0. Do you follow me on this, class? Here, it's really just looking at the circuit this way, which is the same as looking at the circuit this way. Do you all see that S22 will be the same as S11? Give me a show of hands if you do. All right, you're going to scattering parameters. It's important to see this. So that makes this really easy. If I have S11 as that, I know that S22 will be equal to 1/5 as well. Now, here's the ones that people make mistakes on. It's the transmission parameters. And if I look at this for a second, if I want the transmission parameters, which is going to be, I'll put it right here, S21, right? That's equal to V2 minus over V1 plus, correct, class? And again, it's with V2 plus equal to 0. And what I'm really saying is, if I go into port 1, that's V1 plus, right? I want to see how much amplification happens. Suppose it was increased by 10 times. So V2 minus would be 10 times V1. Then S21 would be 10. All right? Does that make sense to everybody? Now, here, how do you get it? Well, the way you get it is first this. We find the impedance we're going into, right? This way. But now we have to find the transmission, really, right here. Well, I have to find the value of tau right there. And tau is really what? It's the amount of the signal that's transmitted into the shield. You remember that? And the transmission coefficient there, I can write it right here. This is in port 1. It would be 1 plus the reflection coefficient, or the transmission coefficient is just 2 times the impedance I'm going into, or 2 times 150, over the sum of the two, or 250. You all see that? The impedance I came from was 100. The impedance I'm going into is 150. Do you all see that, class? So this would be the transmission coefficient. Does everybody follow me on this? Give me a show of hands here. Now this is where it gets different, so pay attention here. So the transmission coefficient is what we need. Now we've got the signal here. Now listen, now we know the amount of signal right there, V1 prime, call it. Follow me? That's the signal just on the other side of the connection of the resistor. Now how much of that signal actually gets developed here? Well, it's like I've got the signal right here, right? That's, call it V1 plus prime. Here was V1 plus, now transmission coefficient times V1 is V1 prime. That's on the inside, that's on the resistor side of that junction. How much of that signal gets over here? Well, now I have to multiply it by 100 over 150 because that's a voltage division now. Do you all see this, class? The problem is a lot of people do voltage division right from here. They just say, well, that voltage is there, so what I'm going to do is just divide V1 by, multiply it by 100 over 150, and that's how much would be over that 100 ohm. That's wrong. All right, you have to include the transmission, because these are transmission line problems or waveguide problems. So it's always how much of that signal gets through and not reflected. All right, that's important. So then it's going to be this times, and now it would be the voltage division would be 100 over 250, over 150. Now what is tau? Well, tau is 1 plus the reflection coefficient, or it's 2 times 150 over 250. So that's 300 over 250, right? Times 100 over 150. So I can say that S21 equals, and that's going to be 2 times 150. I'm going to write it all down for you so I don't get any questions about what I did. And then this is going to be times 100 over 150. Again, the second part is the voltage division. Once the signal gets through, this is the amount transmitted. You all see that, class? All right. Now here, what are you going to get for this? Well, the 150s cancel, right? So I have 200 over 250. Or you could say it's really what, 4/5? You all follow me in this, class? Now, the problem, again, most people mess up is they don't get this transmitted voltage. They ignore that. That's the problem. Remember that. How many read this in the book and saw this? You did? I'm telling you, you did too. It's a tricky thing, and a lot of people don't see it. We'll do another one. So really, by the way, when you have S11, you have S22. When I have S21, I have S12 because it's a symmetric problem. The port parameters are the same on either side. If you spin this around, you're going to get the same port parameters, transmission and reflection. All right, so that's the first problem I wanted to do. Second problem, just like it. When is this rain going to knock off? Anybody know? Tonight? Yeah. So it's going to be. All right. So let's do another one. Matter of fact, we probably can get a problem out of the book. Why don't we talk about the actual problem in the upper corner on 611, page 611. It's the port parameters of some very obvious circuits. So here, they're going to say that they have a transmission line, transmission line, transmission line, transmission line here, here. And the first one is this. This is some Z0. This is Z0. This is port 1. This is port 2. The first one is this. So it's a straight connection right through there. When you see that, if you look at this, what is S11? Well, it's the ratio of V1 minus over V1 plus, given that V2 plus is 0. I want you to take a look at this. Isn't effectively this just connected to the other side, class? Do you all see this? So what's the reflection coefficient? It's 0, right? It's 0, and we know because if we take Z0, the impedance I'm going into, minus Z0, the impedance I came from, over the sum of them, it's 0, class. You all see that. So this is 0. What is S22? Just by looking at that. Well, it's technically, it's going to be what? V2 minus over V2 plus, given that V1 plus is 0, correct? What is it by looking at it? That's a reflection coefficient in the second port, isn't it? How much is reflected from what came in? It is 0, right? Nothing is going to be reflected. You can effectively take these two and fuse them together. There's nothing resistive between them. All right? So that's 0. Now what's the transmission property, S21? Well, that's V2 minus over V1 plus, given that V2 plus is 0. Look at it and just think. All right, how much of a signal comes out here? If I put V1 here, plus, and it's moving this way, how much of that comes out here for V2 minus? Class? All of it. You all see that? There's nothing reflected. It all goes through. So this one is equal to 1. And how many see Z1, 2, which is equal to V1 minus over V2 plus, given V1 plus is 0. What's that? Well, it's how much of the signal, if it's coming from the positive, from V2 positive into port 2, gets through to port 1. How much? All of it. So this is 1. Correct, class? Now, I'm showing you, this is a very simple one, but you take a look at this, and things start becoming clear as far as what these port parameters really mean. I didn't put any active elements, any amplifiers in there. I'm going to try to later in this course, because then you'll see how really you do microwave design in a big way. This is one. The next one that they do is going to be the open. All right? So now I take a look at this next one right here. It's an open circuit, like that. All right, that's an open circuit. Now, I want you to think about this for a second. What's the impedance this transmission line sees this way? It's infinite. You all see that? It's cut off, right? What's the impedance this one sees? Infinite. And by the way, just by looking at this, you don't have to do a single calculation. How much of the signal from this port gets to this port? 0, right? So that automatically, without going through any calculations, you can see that S21 equals S12 equals 0 for that circuit, just by looking at it, right? Because the S12 and S21 are the transmission properties. How much from one port gets to the other port? That's where amplification comes in if you have an amplifier. All right? How much is going to be the S11? That's V1 minus over V1 plus, given that V2 plus is 0. Now think about that. Isn't that the reflection coefficient? That's the definition of the reflection coefficient on port 1. And what is it? What's the impedance I'm going into? Class? Infinity, right? So you could call it really infinity if you want. Minus Z0 over infinity plus Z0, which is 1. It's really in the limit as it approaches infinity. You follow me on this, class? What do you think S22 is? 1, right. These are real good so you start seeing it. We're going to go to the next one. By the way, I have not done this, but I bet money, if I give some of these on a quiz, just these 4 setups, you'll get people messing them up because they don't want to, they almost get panicky. Oh, it can't be that simple. It is that simple. It really is. It's as simple as you think. So the next one, he does this, shorts it. All right, get rid of that. Let's see how you're doing this. All right, class, here's your time to have a little fun. Now I'm going to short it. All right. Now I want S11. Well, technically that's V1 minus over V1 plus, given that V2 plus is 0, right? V2 plus is 0 necessarily. There's no source. There's nothing that would in any way, shape, or form create a V2 plus. Do you all see that? So if it is 0, and it is, if there's no, I can just say that this is the reflection coefficient at port 1. I want to make that clear to you. You all see that? Now, answer me this. If that's the reflection coefficient at port 1, what is it? Well, it's the impedance I'm going into, right? What's the impedance I'm going into? 0 minus the impedance I came from, Z0, over the impedance I'm going into, 0 plus Z0, or minus 1. You all see that? For this one, without doing a calculation, what is S21, which is S12? Take a look. Class? 0. It's 0 because none of the input signal from terminal port 1 can get to port 2, and vice versa, right? From port 2 to port 1. Do you all see that? So that's 0. These are simple, but people will make mistakes, especially this part right there. I'll get a 1 instead of a minus 1. Right? It's a minus 1 because it's a short. That's the reason. If it was an open, it would be a plus 1. That's the example before. Then the next one, this is the odd one I like. I like what Stu did on this one. We'll keep going on this and just add some different things. So the next one, he has this. He has port 1 being open and port 2 being a short. All right, just take a look at this. Now, we've got all the tools to do this one based on the prior stuff we did. But for the start, what is S21 or S12, just by inspection? How much of the signal from port 1 can get to 2? How much from 2 to 1? It's 0. These are transmission. I'm trying to get you acquainted with the fact these are the transmission properties from one port to the other. If there's no connection, there's no way any signal gets there. That's the beautiful thing, that you don't have to do a calculation. Now the next part is what? S11 is equal to V1 minus over V1 plus, given V2 plus is 0, right? Well, V2 plus, even if it was non-zero, it wouldn't matter. It can't get over to port 1, right? So this is really the reflection coefficient of port 1. What is the reflection coefficient of port 1? We just did this. We're going into an infinite impedance. It's 1, right? It's 1. All right, what about S22? Now that's negative 1 because it's a short, right? So we've gone through the basic modeling that he's got there on top of, the basic, what do they call those? The binary decision making, where you either have a short or an open on the ports. And he went through it. And he does a good job here. Next one I want to do, I'll put it here too. I'll leave it like that. And do one with a little more hardcore stuff. All right, I'm going to do one 10.27 next. It's going to have a capacitor, 2 picofarads into a 50 ohm line at 1 gigahertz. So now we're just going to put a capacitor here. And C is equal to 2 picofarad. The frequency is going to be 1 gigahertz. Right? Now I want to calculate these parameters. And this is starting to get just slightly more complicated. We're just doing this in I gradually increasing the complexity. So here, the thing I need to do is get an impedance for that capacitor, right? I don't need a C value. I need a value of impedance. So when I think about the capacitive reactance, it's equal to minus J over omega, which would be 2 pi times 10 to the actual 9th, times C, which is 2 times 10 to the minus 12, 2 picofarad. And what is that going to be? X sub C is minus J over, and then I have 4 pi, right? And then I'm going to have 10 to the minus 4, which be 10 to the 4th here. So what is X sub C exactly? Minus J what?
80.
What?
80. Like 80.
It's 80?
Close enough. I call it 80. 79.5.
80 it is. Yeah, I'll grant you that. All right? Okay, fine.
What number is that? 24?
27, 827, sorry. This is problem 827. All right, when I do this one, now I'm going to go ahead and get the parameters. So first, you'll know that from the port 1 side, what it looks like is going to have the actual Z naught, and that's a 50 ohm line, I think, in this problem, as I recall. 50 ohms. Then I have a capacitive reactance here of minus J80. I'm going to leave it as minus J80. And then it comes in right here to the transmission line where this is port 2, where this is going to be 50 ohms as well. So when I look at S11, and I'll put it right here, S11 will be equal to the impedance I'm going into, right? It's really going to be V1 minus over V1 plus, given V2 plus is 0. Do you all agree V2 plus is 0? There's nothing coming in that port, right? You assume it's matched load. So when I look at this, this is a reflection coefficient of port 1. And that reflection coefficient is going to be the impedance I'm going into, which is going to be what? Quantity 50 minus J80, right? Right? Minus the impedance I came from, which is 50, over the sum, which is 100, minus J80. Do you all agree with me there? Right? Impedance I'm going into is 50 minus J80. Impedance I came from is 50. And when I sum them together, I get 100 minus J80. Now, you can see the 50 goes away on top. So I'm left with minus J80 over 100 minus J80. Now you'll notice this has a magnitude and an angle. It's not just real. This is important. So when you get this one, what is it? In magnitude and then an angle. Anybody?
0.625 at 129 degrees.
Is that what the book has? Anybody? I think I posted the solutions, right? I put them up there, didn't I?
No, I left off negative, so 180 degrees off that.
All right.
Minus 51.
Yeah, that would be minus 51 degrees. Fine. Minus 51 degrees? Class? All right, fine. That's good. That's S11. How many see that that's going to be S22? Raise your hand. Y'all see it's symmetric, right? You can just take this and spin it the other way, and it looks the same. So now we got S22 is equal to S11. All right, good. Keep going on this one. The next thing I need is, I want the transmission coefficient. Now, tau is equal to 1 plus the reflection coefficient, tau at port 1, right? This is going to be the transmission coefficient, right? It's 1. Just add 1 to that, if you don't mind, if you still got it in your calculator. Anybody?
1.47
Angle of minus what?
19.3.
Okay. So that's tau. And now when I go ahead and look at S21, that's V2 minus how much comes out port 2 over V1 plus, what relative to how much comes in port 1. So it's V2 minus coming out, V1 plus going in. It's the fraction that's actually coupled to the port 2 from port 1, assuming V2 plus is 0. When I look at this, first thing I have to do is get the transmission coefficient in port 1. Now, when you do that, it says if there's V1 plus here, there's going to be a plus to minus V1 prime there. V1, call it prime right there. That's how much gets on to the actual filter. Do you follow me, class? That gets across this boundary. There's some that hits and it's reflected, but some is going to get across. All right? So it's transmission coefficient. Then after that, it's voltage division. Then this is going to have minus J80 and that 50. And we just take the 50 over 50 minus J80 to get the amount on that 50 ohm. Do you follow me, class? So then you do this times 50 over, and then it's going to be 50 minus J80. And what do you get for that? If this is the transmission coefficient times 50 over 50 minus J80, what do you get? 38.7, did you say? All right. Now, does anybody have the solutions for these open?
I have checked.
You what?
Check.
I mean, this is that. All right. It's important that you see this. The difference here is complex numbers, right? Remember, now we've got complex impedances. I'm going to tell you one other thing. This is a symmetric network. There's a way to actually do, you can play with, if we actually take the S matrix, he has certain things where you say it's symmetric if certain things occur. The way you tell symmetry, just see if you spin it around, it looks the same. It's a symmetric network if that's the case, right? That's the only thing I tell people. I don't worry about looking at the S matrix and doing any kind of matrix rules on it. I never have. Most people don't. The only time we're going to do things with matrices with S parameters to see the amount of loss, and that'll come later, if we want to see the total amount of loss within the network. And if there are no resistors in the network, there is no loss. That's the bottom line, because capacitors and inductors don't have anything lost. Now we're going to do another problem. My gosh, time flies. I just want to do one more, but I want to do one that's got two elements. Now you can have as many elements as you want, but two is usually all you need. So suppose I have this. Then you'll get your quiz. I know you're worried about that. All right, here we want to get the transmission parameters, the S parameters. You can see it's not symmetric. It looks different this way than that way. Do y'all follow me in this class? It's important you do. If you wanted S11 on this side, thing you would do, first of all, would be to take V1 minus over V1 plus V2 plus equals 0. Well, that's fulfilled here. There's no way anything's going to come back, right? If I had time, I'd show you an example of when something will actually reflect back, and that's with a short circuit here. Then some of that waveform would hit and be reflected back. But that comes a little bit later. When I do this one, by looking at what would it be? Well, it would be the impedance I'm going into, right? You all see that's going to be R1 plus the parallel combination of R2 Z0, right? Over minus the impedance I came from. So I'm just going to write this in terms of general terms. So the impedance I'm going into would be R1 plus, and then it would be R2 in parallel with Z0. That's the impedance I'm going into minus Z0 over, then it's going to be Z0 plus R1 plus R2 in parallel with Z0. And that would be S11. Do you all agree with me? For any values you choose to insert. Agree, class? What would be S22? S22 is going to be V2 minus over V2 plus, given V1 plus is 0. There's no short circuit here. There's no way anything going through port 2 is going to reflect back. So when I take a look at this, what's the impedance I'm going into? Take a look at it. It's going to be R1 plus Z0 in parallel with R2. Do you all agree with that? Take a look. An impedance I'm going into for port 2. It's going to have R2 in parallel with the series combination of R1 plus Z0. So this is going to be equal to the parallel combination of R2 in parallel with R1 plus Z0. That's the impedance I'm going into. Minus, it's going to be the impedance I came from, which was Z0, over the sum of the two. So it would be R2 in parallel with a combination of R1 plus Z0 plus Z0. And that would be S22. Do you all follow me on this, class? Always impedance you're going into minus impedance you came from. All right, what about S21? Well, that means now I need to find how much of V1 plus, right here, going this way, actually appears here. So I need the transmission coefficient times this first. You all follow me? So I'm going to just write this down. It would be the transmission coefficient in port 1, which transmission coefficient is 1 plus reflection coefficient in port 1. And then it's going to be the voltage division between what? This is where the voltage is developed, the parallel combination of those two over the parallel combination of those two plus R1. So it's going to be this times the parallel combination of R2 in parallel with Z0 over R2 in parallel with Z0 plus R1. That would be S21, and S12, just for the record, would be what? Now, we'd need to get the transmission coefficient going this way, right? And that's 1 plus the reflection coefficient on port 2, which is this. So that's going to be tau 2. And once I have the signal developed here, right? Now I need to find the amount getting out that, and then would be the voltage division between Z0 over Z0 plus R1. So it's this times Z0 over Z0 plus R1. Do you all agree with me? I'm trying to make sure you see the simplicity of this stuff. Once you get the hang of it, you got to get transmission coefficient times the voltage breakdown, or voltage division, then you can go. All right, now, that said,